Exactly.
So it went back to like the retro. Oh, but it hasn't all like.
But the new bags don't look like that.
Yeah. So it's different.
It's not. You're deluded.
Okay. Part C of this problem was to find the total distance traveled by the particle. So we have the integral from 0 to 2 of v of t is equal to, and we're going to break up the integrals into the individual pieces. So from 0 to 1, and then it'll be minus because of the left from 1 to 2. So integral from 0 to 1 of 6t squared minus 18t plus 12 minus the integral from 1 to 2 of 6t squared minus 18t plus 12. And we had already found this in an antiderivative up here, so don't reinvent the wheel. I'm just going to rewrite it.
Oh, yeah.
So 2t cubed minus 9t squared. Oh, it's right there. Plus 12t. Evaluated from 0 to 1. Minus 2t cubed minus 9t squared plus 12t from 1 to 2. So if I plug in 1 for t, what do I get?
So let's think about it. That's like 3. Wait, you said plug in what number?
1 for t.
Is 5.
5. Plug in 0, I get 0. So 5 minus 0 for that one. Minus this next one, plug in 2. You didn't put the negative sign on here, right? Okay, just making sure. And then for 1, we got 5 from before, so minus 5. So that's 5 minus negative 1, so 5 plus 1 is 6.
I forgot. What are what exactly is the 6? Like, what are we finding for C?
This was total distance traveled.
So we don't have to do like units.
No, because it doesn't give us units. All right, I'm going to jump to the next thing just because these problems are so long. If we feel like after y'all start doing them that we need to do another one, we can go back and do another one, but
But they're, very repetitive. So like,
yeah. I mean, the process is pretty easy overall, I think, so probably the hardest part is B, just because you have to remember to do the initial position plus the displacement. But otherwise, it's, most time consuming is A, but. All right, number 10, this is one we're going to need our calculator with NINT. Just because it's a type of problem that you don't know how to solve yet. So, we've got a particle travels with velocity v of t is equal to t minus 2 times the sine of t in meters per second for 0 less than or equal to t less than or equal to 4 seconds. So this one does have units on it, so we would be using units for this one. But the other one, since there's no unit specified, we don't have to worry about that. Or, well, the other ones, I guess they technically says velocities in meters per second, but when the book does the answers, let me make sure. Yeah, they don't use units, so. But these ones do use units, so I guess when in doubt, you can put units, it's fine, but you don't have, it's fine, so. A, what is the particle's displacement? So ordinarily, to figure this out, okay, this would be like the equivalent of part B up here minus having an initial position at 3. So we have to integrate the function that we're given. So this would be the integral from 0 to 4 of t minus 2 times the sine of t dt. But the problem is, do you know how to integrate that?
Use substitution.
I mean, doesn't.
So if I do use substitution, what's going to end up happening? Like, what would you choose for u?
T minus
That's in the parentheses, but that's what I.
So if you chose t minus 2, that means that du is just 1. But then you still have a t and sine of t because that in there by itself. And if you just choose t, then it doesn't really help you because then you still have u minus 2 in the front. So this would actually have to be integrated by parts, which is doing a u, du, a dv, and v. And so that's not something that you know how to do, because we don't have to do that in AB. So we're going to use NINT for this. So you'll put that into your calculator. Obviously the t's will have to be x's when you put it in because the way that it's in there. But and it's just going to produce a number for you.
You say we can substitute the t for x.
Yeah. Like, you can
Yeah.
only really put, I mean, how do you get to the other, like?
You have to completely change the mode of your calculator, which I've done once, and that was when I did polar in pre-calc a week ago. Like, I had never done it prior to that.
I got negative 1 point. How far do you want me to go?
Let's do 2 decimal places.
Okay. 1.45.
And this would be in meters. So this would be the displacement of that. Now, in case you're just so interested to want to know what it would look like, if you did it by parts, that's how you would do it. You basically have to pick something to be your u, something to be your dv, and then you work, like, the u part works the same way as u substitution, but when you find the dv, that's something that you have to be able to integrate, and so that's integrated back, and then there's a formula for it for doing that. So that's how you would have to do it by hand, but we don't do that in AB calculus, so no need to worry about that. Okay, now I have to look at part 2 and make sure that part 2 we can actually do, because I didn't. So part 2 says, what is the total distance traveled? Now I'm trying to look and make sure we can actually do this. This is the problem with our book being something for both. So total distance traveled in general would be the integral of the absolute value of v of t, and obviously whatever the parameters are. So for our situation, it should be the integral from 0 to 4 of the absolute value of t minus 2 times the sine of t dt. Check here and see if what I think works. Don't die. I must still be in parametric. Oh dear. Or polar, I mean. Okay, there we go.
I think you just need attention. Sure.
Okay. All right. So this one, because again, we still have the issue of not knowing by parts. What you have to do when you enter it this time, and you can't just do this at the end, it's got to be done at the beginning, is you've got to put the absolute value bars around the piece in there. Okay, so if you've already, if you still have it typed in, you can hit second entry and then just insert absolute value bars. Or you can just retype the whole thing in. But you've got to have that stuff in the absolute value bars, and then make sure you close your parentheses around the sign of, it'll be X for what you're typing in.
Where are absolute value bars again?
Hit math and then arrow 1 to the right.
Oh, for a number? Oh.
Yeah.
Oh, okay.
And it'll either write it as ABS and then in parentheses, or it'll just give you anyway, it'll put the bars there. That's what I was trying to say. words weren't wording.
I got 1.9.
Yeah, it takes a little bit because it has to process the absolute value.
Yeah, I took
Like the integral of that, because again, not something that you know how to do.
Would you have to do that by parts?
Well, the integration would still have to be done by parts to do that, but then after that, you would have to. So basically, we would have to do what we did up here in part like A of the previous questions, where we found where it was stopped, and we would have to do intervals, and we would have to break it up and do each individual interval and get it. So like the way this one would have ended up working if we had done it by hand, which again you wouldn't be able to do, but it would have been an integral from 0 to 2 plus an integral from 2 to pi plus an integral from pi to 4. But because you don't know how to do by parts, we can't do it this way. And then what this would have done is we would have solved each integral individually, and this would have given you the absolute value of negative 1.09. This would have been the absolute value of 0.23, and this would have been the absolute value of 0.59. And then we would have added all those together and gotten the final thing that way. But unfortunately, I think that's the only one in here, a problem like that. And it's by parts. So, but we could have done a similar thing. I mean, this is basically what we did up here. It's just doing it as more of a word problem instead of just giving you a function. Let me see. What is left in here that we need to look at? Is this a review section?
stupid I have a test
All right, we're gonna do number. Well, hold on. Do I want to do that first, or do I want to do this example first that they have? Because I have a note about looking at this example first. All right, we're gonna look at example 6 really fast, and then we'll look at a problem that uses, or that's like from this. So, gotta make sure the iPad doesn't go off. Alright, so there is a pump connected to a generator, operates at a varying rate depending on how much power is being drawn from the generator to operate other machinery. The rate in gallons per minute at which the pump operates is recorded at 5-minute intervals for 1 hour as shown in the table, which is over here. How many gallons were pumped during that hour? And so there's a couple different ways that you can do this. We can do gallons pumped from time 0 to time 60 of R of t, which is the rate. But we don't know R, so because these are all equal time intervals here, we can actually use the trapezoidal rule to do this. So this is kind of going to be an application of the trapezoidal rule that we had from, what was it, 6.5? Which is the problem that we're going to look at is going to be an application of the trapezoidal rule. Because before when we did it, those problems just had us explicitly using it, but now we'll be using it to solve something. And so that integral would be approximately the same, because remember that's what we found is the trapezoidal rule. While Simpson's rule was more accurate, trapezoidal rule still gets you to a similar answer of 60 divided by 2 times however many numbers there are. I think there was 12. Maybe, I don't know. I didn't count them. Anyways, trust the number. And then the first number in the table, so 58 plus 2 times the next one plus 2 times the next one, so on and so forth, all the way down till the final one. We just add that one as is, and then we get our final number when we multiply that out to be 3,580 gallons. So we're gonna do one like that in regards to I think it's milk.
I might need a review of the trapezoidal rule. Different.
That's what we're getting ready to do. So. So, 27 is going to involve the trapezoidal rule. So it says we have and you might want to have your book open to page 391 to see the table. I'll write it out and set it up so you don't necessarily have to have it, but if you want to be able to see it. A machine fills milk cartons with milk at an approximately constant rate, but backs up along the assembly line, cause some variation. So sometimes they get backed up, and that's what they're saying is like where the variation can come from. The rates in cases per hour are recorded at hourly intervals during a 10-hour period from 8 a.m. to 6 p.m. Use the trapezoidal rule with n is equal to 10 to determine approximately how many cases of milk were filled by the machine over the 10-hour period. So a couple things about the trapezoidal rule. H is equal to B minus A over N. And the trapezoidal rule itself says that H over 2 times Y sub 0, so that's the first number, plus 2 times Y sub 1, plus 2 times Y sub 2, plus plus 2 times Y sub n minus 1, plus Y sub n. So the final number and the first number are not multiplied by 2. Everything else is, and they're added together. And they told us in this problem that n is equal to 10. So we have B minus A over N. Oh, wait. 1, 2, 3, 8, 9, 10. Okay, so let me show you this so that you can see this. This is a little misleading because this is the time of day that this occurred, not like how long something took
Okay.
in this particular chart. That's not always the case, so make sure you read the chart to understand it.
8 o'clock, 9 o'clock.
Yeah, because it starts at 8 a.m. and it goes till 6 p.m. So we're looking at how many like hours passed in this. They tell us it's a 10-hour period. So that means that B minus A is equal to 10 because this was a 10-hour period. So B minus A is equal to 10. So that means when we find H is going to be equal to 10 divided by N is 10 also. So that means that in this case, H is equal to 1. So then now, plugging into the trapezoidal rule, T is equal to, well, H was 1, so 1 over 2 times. Now these Y values are from the right side where the rate is given to us. So the 120 will be by itself, and then this 121 at the bottom will be by itself. Every other number in here is going to be multiplied by 2. So it's going to be 120 plus 2 times 110 plus 2 times 115 plus 2 times 115 plus 2 times 119 plus 2 times 120 plus 2 times 120 plus 2 times 115 plus 2 times 112 plus 2 times 110, and the final one plus 121.
I got 1,156.5.
Did you say 0.5?
Yes.
Okay. Just trying to make sure I was writing as you said it, and then I was like, did he say 5 something else or something else 5? And this would be cases for the 10-hour day. So that's how many cases of milk that were produced in that 10-hour period, approximately.
Does our answer have to be in significant figures?
No. All right, I'm going to jump back, I guess, to example 7 on page 389 in the book to look at about Hooke's Law, and then we'll do an example of Hooke's Law, and then I'll give you a few problems to work on. So Hooke's Law here is, obviously we've done this thing in physics already, but force is equal to K times X. And so we've got this problem here. So it takes a force of 10 newtons to stretch a spring 2 meters beyond its natural length. How much work is done in stretching the spring 4 meters from its natural length? So we let f of x represent the force in newtons required to stretch the spring x meters from its natural length. by Hooke's law, f of x equals kx for some constant k, and we're told that f of 2 is equal to 10, which is equal to k times 2, so that means k is equal to 5, or f of x is equal to 5x for this specific spring. So construct an integral for the work done in applying a force over the interval from 0 to 4. And so you can do it as a Riemann sum and set it up by, doing all this fancy stuff, the summation of all of that. But we can also do it with integration and doing it that way. So the limit of these sums as the norms of the partitions go is 0. So this is a little different than how we're going to do the problem that's in the book, but just for you to see it. So we're looking at from 0 to 4 of f of x dx. So we plug that in, we integrate it from 0 to 4, and we get the total Newton meters of force, or work done, And this is when you get to appreciate that we got to do it with basic algebra instead of with calculus when we did it in physics class.
So is this what I would be doing if I had to do like the university, whatever it's called?
Yeah. All right, so we're going to do number 30 about Hooke's law here. So, Hooke's law also applies to compressing springs. So the one we just did was a stretch. This one's going to be a compression. It requires a force of kx to compress a spring a distance x from its natural length. Suppose a 10,000 pound force compressed a spring from its natural length of 12 inches to 11 inches. How much work was done in compressing the spring? And then it's part A says the first ½ inch. So basically to get it from 12 inches to 11.5 inches, we were looking at that first, and then we'll look at the second ½ inch, so 11.5 to 11.
That sounds like physics.
It is.
But just in physics, we can use basic algebra and calculus for it.
So this tells me that the 10,000 pounds is K. So, I guess you end up finding that out. I don't know if you didn't technically know that yet, but oops.
Oh.
Because F equals KX, the force is 10,000, which is equal to K times the distance that it is compressed is 1. So K ends up being equal to 10,000 also. So this is technically the force here, but K is also 10,000. Once we solve for it. I just got ahead of myself and gave you a little spoiler there. So now I am going to integrate for the first ½ inch, but I don't have to do from say 11.5 to 12, right? I can do from 0 to a half and make my life easier. So I'm going to integrate from 0 to 0.5 of 10,000 x dx. And if I integrate that, what do I get?
X to the 10,000. You mean like take the answer and bit? 5,000
5,000x squared.
squared. Yeah, I just realized that.
I was like, that would be a lot. X to the 10,000. Pretty crazy. And this is going to be evaluated from 0 to 0.5. Obviously the 0 is 0, so whatever when you plug in 0.5 is going to be the answer. Any guesses on my units?
Let me guess.
Newtons, joules, Newton meter squared.
Maybe pay attention to what was given to me to begin with.
Foot pound. Inch pound.
Inch pounds.
Really?
What? I don't like that.
What?
Because this was given in inches and our force was in pounds. Normally our force is in newtons.
I don't like how that sounds. Is that like United States kind of? Like
Yeah.
Inch
This
pound?
is our nonsense here in
Know
America.
that before.
America.
Dude.
That's so American.
That is so. America.
Oh, there's a bee.
This is.
I thought you saw a bee and I was like, where?
Oh no.
Because I have had a wasp in here before because there's a hole in that window and it flies in
Really? Where?
in the bottom.
I had a wasp get into our apartment one time, and I waited for it. The window was open, so I waited for it to go under the window, and I slammed the
Did I
window
tell
down.
y'all-
So
did
it suffocated and died.
Did I tell y'all how I made like the easiest $100 of my life?
No.
Yes, you did.
Oh, I didn't hear. How'd you make the easiest $100
I
of your life?
told you. I crushed a wasp nest with my hands.
Peyton was absent.
No, I was not here for this.
Yeah.
What? You
When did you do that?
crushed a
Oh, you told us in English.
Oh, it was in English?
wasp nest?
Yeah. Well, my brother, we were doing yard work. I
Who
think
gave you
this was
$100?
2 weekends ago. And Gary was like, I bet you $100 you won't go up to that, like, active lostness.
Did you get stung?
No, I was out of there real quick after I crushed it.
How did that?
You had time to crush it and get out of there without getting stung?
Yeah, well, there were only like 4 wasps on the nest. So I just like
He actually gave you
crushed it
$100?
like that and I ran. Yeah. $100. Easiest 100 of my life.
I don't think I would classify that as easy.
Yeah.
It was very easy. It took minimal effort.
Alright, the second half inch will be 0.5 to 1 of 10,000 x dx. Nathan, do you want to try the integral of this one again?
No thanks.
It's the same thing. 5,000 x squared.
I wasn't thinking.
From 0.5 to 1. So if I plug in 1, what do I get?
Wait. I said wait so that they
We're waiting.
Plug in for X.
Alright, let me finish writing this down before I just start.
Plug in for X.
I hadn't finished understanding what was said. She just said it was the same, so I kind of thought it was going to be the same answer. Sorry, I wasn't listening. The first answer we got. So what are we doing?
Plug in 1 for X.
I wrote it wrong.
So 5,000 times 1 squared. Okay, is 5,000.
I had it finished.
What if I plug in 0.5?
I can't multiply.
And then 5,000 minus 1,250 is 3,700.
3,750 inch pounds.
Inch pounds.
Get that out of here. I can't. I don't know if you do great.
Especially like the suicide hotline.
What?
You be calling the suicide? You okay?
What?
You be calling the suicide hotline? You okay? No, your AirPods.
Oh, through your ear.
He didn't answer you yet, Peyton.
No,
Yeah.
he never said he was okay.
Those callers like make bank. Like I think they get like $60 an hour.
Well, I mean, they're trying to help people not kill themselves. So I
Yeah,
think-
yeah,
I wouldn't want to do that. Cause I'd be like, I don't know.
Don't kill yourself. Time will do it for you.
No, Josh. They would end up killing themselves if you were their caller. You'd be like, if it's time to go, it's time to go.
Now, number 9 is acceleration, and it's trying to get you to velocity, whereas we've been doing velocity trying to get to position, so it should work the same way. Like, it's just, the wording is different, because there's not an exact same problem as
See,
that.
if you wouldn't have said that, I'd probably be confused for a few minutes.
I'd be like, what am I doing?
I'm like, wait.
29, you may need to refer back to that example number 7
Oh.
for Hooke's Law. Yeah, for some reason there's only one of those trapezoidal runs in that part, but then in the extending the ideas section of the chapter, number 37 is one of the trapezoidal ones also. And it should just still be like use the trapezoidal rule to do it. Even though it says other things with it, but it should be that. So
So 37 is trapezoidal?
yes.
Okay.
So yeah, these are flipped from the order that we did them in the examples
Okay.
of how to do that.